Good afternoon. Thank you very much for joining this AIP Open Seminar. I'm Yuji Matsumoto, a leader of knowledge acquisition team. And before starting this seminar, there are some important notice. As you can see, so reproduction is prohibited. So, and also reproducing all or any part of the content is prohibited without the author's permission. But this seminar will be recorded and the video will be available on the RIKEN AIP website later. And another important notice is if you have any questions or comment, please write down in the QA tab. You can see the QA tab, and if you press that one, you will see small windows for QA. And so please type your QA in this box so that I will read your questions and answer questions. Okay, because the QA tab is not can see in the video, so I will read a comment for you. Okay, so let me start my presentation first. So I'm Yuji Matsumoto, and I will introduce the overview of my team. And again, thank you very much for joining. And okay, the main objective of our team is actually the application-oriented group in RIKEN AIP, and the mission of our team is to acquire some knowledge or extract information from any document, but we now focus on extraction of information from scientific papers. Okay, and this slide shows the background. Okay, as you know that there are lots of papers published, so we are faced on the rapid increase of scientific or technical documents, and the number of scientific papers are quite large, and there are actually several hundreds of millions of papers available, and even in semantic scholar page, there are more than 180 million papers. And 1,000 papers are published monthly or daily in many specific domains. And as you know that after the pandemic, Allen Institute of Artificial Intelligence started to collect COVID-19 and related coronavirus papers. And the size of the papers at the moment is a little more than 400,000. Okay, so it's actually impossible to researchers or any of us to read or retrieve all the saturated papers. Okay, and at the moment in our team we have joining two big project. One is the JST CREST project named Knowledge Discovery through Structured Data Document Understanding. We started that about 5 years ago, and this project is almost the end. So this project will end in March this year. And the aim of this project was to conduct a basic research for knowledge extraction from scientific document. And we organized some representative researchers in the field, and we organized 7 teams to tackle this problem. And the main main contents of this talk is about this project. Okay, and another project we started about 1.5 years ago was a NEDO-supported project named Structured Knowledge Extraction from Material Science Document. And it is quite focused project to extract properties and synthesis process information from polymer-related papers. And at the moment we are working on Japanese document. and maybe we will move to English document. Okay. So in the CREST project, we set up five major techniques to analyze scientific document. One is to analyze documents themselves. And in many cases, scientific papers are published in the PDF format. And the PDF format is human, customized, or it is quite useful for humans to read the paper. But for machines, it's quite difficult to understand because they are not so logically structured. So from the PDF, it is not the simple task to extract text and the tables of figures or some other expressions because they have just their positional information included in the PDF. Okay, and even though we extract the text part, usually the scientific document, the expressions or sentences tends to be quite long and complicated. So the natural language analysis is quite important. And another topics we conducted was search, extraction, visualization, and inference. Okay. And in this talk, I will mainly focus on extraction, how to extract the information from the document. And another important thing is how to visualize them. Okay. And another one is to inference. That means not only extracting the information from the document, we need to combine them, maybe to find out hopefully a new information. But in this talk, I will mainly focus on extraction and somewhat of visualization. Okay, and the search for the paper. Okay, and this is the overview of the project organized into basic techniques and application. And for basic techniques, as I said, we need to extract the information from PDF. And in this case, this is a PDF structure analysis to extract text part and tables or figure part. And from both form of information, we need to extract some important concept and relationship between them. Okay. So that is the extraction part. And okay, I will tell that in later. And another is application. And I'm not going to talk about all of them because some other works are done by other members in the project. Okay. So I will, in this case, I will talk about relation-based paper search system, which is implemented by using a basic techniques to extract terms and relations between those terms. Okay, so I will go into next one. And this is a slide for explaining a little bit more detail about data extraction from PDF. Okay, so first one is to structure analysis of PDF document. Okay, now if the papers are formed into XML or some such logical structure, the extraction is not so difficult. But from PDF, we need to first extract the information and need to convert them in some logically structured format like in XML. Okay, and after extracting information, mainly we focus on text part. But from the tables or figures, there are a lot of useful information for describing the relations between entities or properties of the entities. And after extracting a text part, the important thing is to recognize named entity. It's an important concept and relations between them. Okay. And those informations are expressed in a very complicated sentence. Okay. So sentence analysis is another important topic. And as in many of the this kind of field, machine learning approach is used. So in this case, we need to construct some annotation data, or if such kind of annotation data is not available, we need to think about some semi-automatic annotation or semi-supervised method. Okay, and this slide briefly shows the knowledge extraction method. And extraction from of the knowledge from scientific paper is divided in some subtasks like named entity recognition and relation extraction. And named entity recognition means to identify technical concept written in a document. And in many domains like biological domain or material science domain, there are lots of existing database. So from the database, we can easily extract terminologies to construct a dictionary. But dictionary matching is not sufficient because a number of new technical terms and concepts are produced daily. And even though there are, even for the existing concept or existing materials, their names or their writings may be formed in the various ways. So, and there are also the synonym problems, and it is almost impossible to collect all the possible way of writing some concept. So some machine learning based supervised or semi-supervised approaches are necessary. And another important information is represented as relations between named entities or properties of named entities. And there are lots of possible relationship, and each of the relationship can be expressed in various ways. Okay? And in some cases in the document, some important entities may be referenced by pronouns or general phrases. So in such case, we need to identify the antecedent of those properties, or which phrases actually represent the same concept. And this figure showed us some example of the named entity recognition, where each colored box corresponds to named entities, and each of the arrows corresponds to relationship between the entities. So by reading this kind of sentence, we need to find which is the terms that express some concept, and terms may be represented not only by a word, but by multiple words. And there are lots of possible relationship between those concepts. Okay, and once we can do named entity extraction and relation recognition, this is one of the applications we conducted in, this is actually conducted in the NEDO project, but we started this kind of task in the CREST project. So this is an example of material science paper. And within this paragraph, there are a lot of concepts colored by colored box. And in this case, there are four types of entities: material, process, quantity, and method. And there are 5 types of relationship. And by finding entities in this paragraph and finding out the relationship, although it is not directly written in the document part, but if we identify relationship between those concepts and extracted all the recognized information, maybe we can construct this kind of structured knowledge. And in this case, this extracted one on the right-hand side actually describes the synthesis process of the material introduced by this paper. So you can see that some input like Cu, Fe, and S are sealed and heated and quenched, and finally it is synthesized into this new material. And there are a lot of conditions or atmosphere under these processes. So this is kind of information we like to extract from the paper. Okay, and recently, or last 1 year after the pandemic, we started to apply the method we have developed to COVID-19 data. And there is a data set called COVID-19 dataset. This is a COVID-19 related open data collected by Allen Institute of Artificial Intelligence. And the documents are collected from those list of knowledge sources like PubMed or research articles from WHO, bioRxiv or medRxiv. Okay, and okay, this is a little bit old slide. As I said, nearly half a year ago, there was 200,000 papers collected, but now it's almost doubled by 400,000 papers. And you can find those, or you can obtain those papers from this site. Okay, so we obtained those ones and tried to implement some system to retrieve papers based on the information extracted from the paper as a relation information or named entity information. So we applied some existing relation extraction methods and also named entity recognizer and implemented some retrieval system. And I will show you this system. Okay, this is a home page of the system, and we provide two kind of searches. One is relation search and another is graph search. Okay, and the relation search is quite simple one. Okay, you can input some named entities or technical terms directly, and so two entities, and you can input some relations expressed by some words like rees. Okay, so this means that you can describe some relationship between two entities, and then the system searches for the papers which describes those entities. So the under of this query, you can see the list of the papers that includes the relations you specified. Okay. So another interface is graph interface. And in the same similar type of queries can be written in this kind of graph type format. So in this case, user input coronavirus is one entity. Another entity is not a specific term, but another entity should belong to the semantic type disease. And those concepts are connected by some expression, including cause. Then the system finds all the papers that include those relations. And you can extend the description of relations in a quite complex way like this. So this query shows that there are four concepts: protein, disease, chemical, and the term MERS-CoV. And there are some relationship between them. And the expressions of the relationship is not specified in this case. And after throwing this query, the system finds out some papers, like those two papers. And this paper includes four relationships described by the graph. And this another paper includes those four relationships included in the query. And those results are summarized in this way. Okay, because there are only two papers that includes all those four relationships. So this graph is not so complicated. But if you click some nodes, then the system shows other nodes that is directly related to this node in some paper. Okay, so this is a graph search interface to retrieve one paper which includes some concepts and relationship. But if you like to find some multiple papers that include different relationship, so this query graph shows the relationship between disease and the chemicals is written in some paper, and the relationship between that chemical and the tissue is written maybe in another paper because the color of the edges are different. Okay, then the system shows the result in this way. And okay, if you check one, okay, so you can also see the retrieved papers in this way. Okay, so you described two relationships, red one and green one, and one relationship is included in this paper, and another relationship included in this paper. And how the relationship is described, you can be you can see such raw text in this part. Okay, so there are several pairs of the papers that include those two relationships. Okay. So you can write as any relationship, even a relationship included in more than two papers using this interface. And so this interface. And after the interface, you can see the kind of summarization of the retrieved result in this way. And if you click one concept, then you can see the relationship between those concepts in one paper, in another paper. Okay, so this is a way that we try to use knowledge extraction method to retrieve paper and visualize the result. Okay, so this is one of the applications we have implemented. Okay, so but our main focus is to develop some basic techniques which is applicable to this kind of application. Okay, so this is a very brief summary of our project. And so after this, our postdoc researchers in our team will present their current research. And those topics are quite specific talk. And the first talk will be by Noriki Nishida, and the title is Analyzing Discourse Structure of Scientific Papers for Knowledge Acquisition. And this is the analysis of the structure of the document. And he is mainly focusing on the analyzing the structure of scientific paper abstract. And by analyzing those abstract, maybe you can find the functionality or the functionality of each of the sentence, so that you can know that which part may be the important part within the document, within the abstract. Okay. And understanding the structure of the document, I mean, rhetoric structure of the document, will help to extract information which is described in a quite complicated way. And the second talk will be done by Hiroki Teranishi, and the title is Neural Network Approaches to Coordination Disambiguation. And okay, by coordination expression, it means expressions connected by some conjunctions like and or. Okay, and because, as I said, the sentences in scientific paper is quite complicated, and authors tend to use quite complicated coordinated expressions, as I showed in the example. Okay, so this is just a part of the sentence. Median time to progression and median survival times were 6.1 months and 8.9 months in arm A, and blah, blah, blah in arm B. So this expression includes 1, 2, 3, and, okay, 4 and the quite complicated. Okay, so to understand this one, okay, the authors actually try to express quite maybe 4 or 8 concept, okay, relationship in a very compacted way. And another simple coordinated structure is like breast and lung cancers. Okay, now from this expression, we can find a lung cancer. But actually, this coordinated structure describes breast cancer and lung cancer. So simple analysis may fail to detect breast cancer. It just detects breast. But actually, in this part, breast cancer is important concept, not breast. So to extract or to identify the concept like breast cancer in this sentence, we need to analyze the structure of the sentence. And the expression connected by and or is called coordination structure. And Hirokite Nishis talk about to analyze this kind of complex sentences. So those topics are quite specific to natural language processing, but I hope that you can understand why this kind of research is important to analyze complex documents. Okay, thank you very much for now. So this is end of my instruction, and I'd like to move on to the next talk. If you have any questions or comment, please write in the QA. Okay, for now, it looks there is no question at the moment. So I'd like to move on to the second presentation. So Nishida-san, please be ready for your presentation by sharing your slide.
Hello, everyone. My name is Noriki Nishida. I am a postdoctoral researcher at the Knowledge Acquisition team in AIP. I joined this team in last year, and I am working on discourse parsing or automatic document structure analysis of scientific papers. My presentation will be in 4 parts. First, I'd like to introduce the background of this work. And second, I present our goal and what we have done for this program. Third, I show the experimental result. Finally, I conclude this presentation. Let me begin with the background. This figure shows an example of a discourse dependency structure, which we manually annotated to a biomedical paper abstract. Discourse dependency structure describes how a document how a coherent document is organized semantically or logically. And discourse parsing has been shown to be useful in a variety of NLP applications, such as document summarization, question answering, or sentiment analysis. And discourse parsing can be formalized as a task to build a discourse dependency tree given an input document. A dependency tree is a set of dependencies, and each dependency consists of head node, modifier node, and a discourse relation label between the two nodes. Each node corresponds to close-level contiguous text spans called elementary discourse units or EDUs. In this work, we assume that the input document is already segmented into EDUs. And like machine learning model in other areas, state-object discourse parsers use supervised learning, and they depend on manually annotated discourse tree banks, such as RSTDT. However, such discourse tree banks are expensive and time-consuming to manually create. For instance, RSTDT contains only 385 labeled documents. Furthermore, the performance of discourse parsing drops significantly if the training and test data are obtained from different domains. Therefore, it is an important problem now how to enhance and adapt discourse dependency parsing to a different domain using only small amount labeled data. In addition, recently, the pandemic spread of coronavirus disease 2019 has reached most countries of the world, and a number of papers on COVID-19 have been published. And it is becoming harder for researchers to get useful information from the papers. Thus, it is necessary to extract useful information from the papers automatically. Discourse parsing can be one of the tools for this purpose, but there are no available tree banks in this domain. Therefore, unsupervised domain adaptation is an important problem for discourse parsing. In my previous work, I proposed an unsupervised discourse parsing approach. I used beta-BEM training and used prior knowledge on document structure for initial tree sampling in the beta-B training phase and process. In the beta-B training, I first sampled the initial trees based on the prior knowledge on the document structure. And then I used the sample initial trees as pseudo-supervision and trained the parser on pseudo-supervised data. And I sampled the best scoring tree using the current parser from the unlabeled articles. And this process is repeated until convergence. And this is a table of the results of the previous work. And surprisingly, our unsupervised parser with 4 prior knowledges yields better or competitive performance with supervised parser, even without manually annotated discourse trees. And we also found that prior knowledge made a difference of performance by about 9 points. And from the previous work, we learned that prior knowledge for initialization is very important in unsupervised parsing. And this result is consistent with result in existing papers on unsupervised syntactic parsing. We also learned that finding effective prior knowledge is very difficult, and designing effective prior knowledge is somewhat similar to annotating discourse structures manually. Now I'd like to present the aims and the methods in this work. The goal of this work is to adapt discourse dependency parsing for biomedical paper abstract using automatic annotations with a limited number of labeled shield data. And we also report in-depth analysis on discourse dependency parser adaptation. And we also built a new discourse tree bank for this program. Particularly, we investigate the proxy labeling algorithms for discourse dependency parsing in unsupervised domain adaptation scenario. We assume that a small amount of in-domain labeled data and a large amount of out-of-domain unlabeled data are available. Proxy labeling is a semi-supervised learning approach, and it trains model with unlabeled data. And in proxy labeling, we first train the model with a small amount of labeled data. And second, we apply the weak model to annotate a large amount of unlabeled data. And in this figure, red and blue correspond to annotated or predicted class labels. And then we combine the labeled and pseudo-labeled data and use them to retrain the models. This is the procedure or overall procedure of proxy labeling. And our contribution in this work are as follows. And first, we performed comparative analysis of 4 major proxy labeling methods for discourse dependency parsing domain adaptation, unsupervised domain adaptation. And second, we annotated the discourse dependency structure manually to more than 200 COVID-19 paper abstracts extracted from Code90 dataset. And third, we revealed that relaxing agreement criterion in asymmetric trait training, which I will explain later, is effective. And finally, we report typical error causes of the current discourse parsing system. In this study, we implemented the 4 major proxy labeling algorithms: self-training, co-training, tri-training, and asymmetric tri-training. Self-training is the simplest proxy labeling algorithm, we first train a discourse dependency parser on a small amount of labeled data. Then we use the parser to annotate the unlabeled abstract. And then we combine the labeled and sublabeled abstract and use them to retrain the parser. The main problem with self-training or ST is that there is no mechanism for correcting mistakes of the parser, and the mistakes can be amplified during training. And co-training or CT aims to mitigate the ST's problem by building two different models, and letting them teach each other. And it is proved that co-training can improve initial models using unlabeled data when the two views are conditionally independent given the target label, and each view is sufficient for running the task. However, this assumption is too restrictive in almost tasks. So Cho and Goldman in 2004 showed that it is possible to leverage unlabeled data by using two models with different inductive biases, even if the same seed data, the same view, is used for training the two models. Based on the finding of their paper, we developed two models with different parsing strategies, which we will describe later. And in training, or TT, we begin with training three different parsers. Once trained, we apply the parsers to the unlabeled data. And if two parsers agree on the predicted path trees, then the predicted path tree is used as the pseudo-labeled data for the remaining parser. Each parser is retrained on the corresponding labeled data. So the characteristic of training or TT is to use calculate agreement between different parsers. Sorry. And asymmetric training, or AT, is a variant of training for unsupervised domain adaptation. The different point from TT is that AT uses one model as a target domain-specific model and trains it only on the pseudo-labeled data. And AT can easily be implemented by adding several lines to the TT code. Okay. And previous studies that used training for syntactic parsing determined parser agreement based on the global level structure matching. That is, two dependency trees are agreed if and only if they have the globally same structure with each other. And however, this agreement criterion is too strict that a lot of locally agreed dependencies are discarded, even though they may be useful for running the task. And to utilize the locally agreed dependency information, we relax the agreement criterion and determine parser agreement based on the percentage of locally agreed dependencies across two structures, which is defined in these equations. And we consider the two dependency structure to be in agreement if the percentage of the shared dependencies, RJK, is greater than or equal to an agreement threshold tau. And okay, now I'd like to explain the discourse dependency parsing models we used in our experiment. And we implemented three neural discourse dependency parsers using different parsing strategies, a graph-based parser, and a transition-based shift-reduce parser, and transition-based shift-reduce parser that processes the input sequence from right to left. In our experiment, we use the English paper abstract, so right to left means reading the input in a backward order. And based on the previous work on discourse parsing, we first encode each EDU using embeddings of words, part of speech tags, and syntactic head informations. And we then use the BiLSTM to encode the contextual information into the EDU vectors. And based on based on previous work in discourse parsing, we separate the discourse parsing process into two stages. The first stage is construction of naked tree, and the second stage is the discourse relation labeling. The graph-based parser first finds the globally highest scoring naked tree, t hat, using neural dependency scoring function, SDS, scoring function S. And then the graph-based parser predicts the discourse relation labels for each dependency in the naked tree using another multi-layer perceptron. And a transition-based shift-reduce dependency parser builds the dependency tree incrementally by performing a series of operations until the parser configuration reaches a terminal condition. And parser configuration consists of three elements: a stack, a buffer, and a set of dependency arcs. And we employ the arc standard system and define three types of transition operations: shift, reduce right, and reduce left. And we follow the same two-stage procedure with the graph-based system. So I mean, we first construct a naked dependency tree using a shift-reduce system with neural operation classifiers, and then predict the discourse relations to each dependency in the predicted tree. Following existing work in transition-based neural dependency parsing, we implemented the operation classification module and the labeling module using BiLSTM and multi-layer perceptron. Now I'd like to describe the experimental setting and show the results. And we evaluate proxy labeling for unsupervised domain adaptation of discourse dependency parsing to biomedical abstracts. Scientific papers tend to vary in terms of writing styles by research areas. This is also true for paper abstract. For example, in the engineering field, the background is often shortened and more weight is given to the proposed method part. And on the other hand, in the biomedical area, the background is often more weighted and the acquired knowledge is central to the description. And in this work, we use a paper abstract associated with NLP and the COVID-19 pandemic. As shown in this figure, we first use the labeled NLP abstract to train the weak parsers, and then we use the weak parser to annotate the unlabeled abstract related to COVID-19, and then we combine the labeled abstract and the labeled abstract to retrain the model. And finally, we evaluate the model on the test abstract on COVID-19 area. Particularly, we use NLP SciDTB corpus as a labeled abstract in NLP, and SciDTB is a collection of 742 abstracts, and which do the annotated manually. And as unlabeled abstract, we use a code 90 we use a code 90 dataset, and the code 90 dataset consists of more than 35,000 abstracts from PubMed and so on. And we obtain EDU segmentation of this corpus using a publicly available pre-trained EDU segmentation system. Sorry. And for evaluation, we manually annotated a small set of abstracts in code 19 with discourse dependency structure. We call this dataset code 90DT. We first sampled 200 abstracts from code 90 and then chose 70 abstracts with less noise, such as PDF text extraction errors. And we segmented the abstract into EDUs manually, and we annotated the discourse dependency structure to the abstract, 70 abstract. And we used 50 abstract for testing and 20 abstract for validation. This table shows the characteristics of SciDTB and Code 90DT. The table indicated that texts in Code 90 tend to be longer than those of SciDTB. Please see the rows corresponding to number of sentences and number of tokens and number of EDUs. So, okay. However, so the average number of EDUs are equal between the data set. So it means that EDUs in Code 90DT or Code 90 tend to be longer or more informative than in SciDTB. And the average root EDU's position of Code 90 is more backward than SciDTB. Please see the last row. And this suggests that the research background part tends to be more weighted in Code 19 or biomedical abstract than in NLP abstract. And this table shows the distribution of dependencies in each discourse relation category. So each row corresponds to the discourse relation class. And there are significant differences in frequency distribution for some categories, such as elaboration or evaluation. And these statistical differences suggest the difficulty of adapting discourse dependency parsing from NLP abstract to biomedical abstract. Okay, now I'd like to show the experimental result. This table lists the parsing results on Code 90DT. And for reference, we also show the result on the SciDTB test set. And we can observe that all of the proxy labeling methods outperform the seed data only baselines for Code 90DT. And so seed data only baselines use only seed labeled data. So they don't utilize the unlabeled data. And these results indicate that proxy labeling can enhance and adapt to discourse dependency parsing for a different domain by using out-of-domain unlabeled data. So, and particularly TT and AT is higher performance gains than ST and CT, which suggests that discarding noisy pseudo labels based on agreement criterion is promising for this problem. And moreover, we observed that the relaxation of agreement criterion in try-training or asymmetric try-training is effective. Please compare the result of tau 0.9 tau versus 0.5 tau threshold. And however, we also found that proxy labeling systems, except for TT with 0.5 threshold, do not outperform the seed data only baselines. Please see the last column. And however, if we use NLP abstract as unlabeled data, and whose results are shown in the parentheses inside in this column, proxy labeling systems, except for ST, outperform the baselines. So these results indicate that it is important to use unlabeled data in the same domain with the test data for this problem. Okay, now we examine the connection between the number of labeled data and the parsing accuracy, which is shown as labeled attachment score, LAS. And we found that proxy labeling outperforms the seed data only baselines consistently to the different number of labeled data. And the performance gain by AT, shown in the green line, is more apparent than that of ST, shown in the orange line. And more surprisingly, we found that AT achieved a significant reduction in manual annotation cost over the baseline. So for instance, AT requires only 300 labeled data to achieve almost the same parsing accuracy with the baseline. Please see the black dotted line. And the baseline is trained on the full 742 labeled abstract. So this result indicates that the AT can reduce annotation cost by about 60%. Okay. Now we also investigate the connection between the agreement threshold tau and the number of labeled data, as well as the parsing accuracy. And x-axis corresponds to the agreement threshold, and y-axis corresponds to the percentage of utilized pseudo-labeled data or parsing accuracy. And these figures show that the threshold has a significant impact on the parsing accuracy. And the optimal threshold is 0.5 for labeled attachment score, or 0.7 for unlabeled attachment score. And we suspect that this is due to the trade-off between the size and the quality of the pseudo-labeled data set, and it can be controlled by the threshold. When the threshold, for example, when the threshold is too small, the quality of the pseudo-labeled data set becomes too noisy. In contrast, if the threshold is too large, the size of the pseudo-labeled data set becomes too small to adapt to discourse dependency parser. And we also analyzed the parsing errors. We found that most of the errors are caused by 3 factors. The first factor is the data sparsity problem in discourse structure patterns. And these figures show the confusion matrices of the parser outputs, and each for the dependency distance, length, and the relation levels respectively. And these figures show x-axis corresponds to the predicted dependencies, and y-axis corresponds to the goal dependencies. And according to the left confusion matrix, and 90% of the adjacent dependencies are correctly identified. So I mean dependencies of length 1 is correctly identified. And however, only about 60% are accurate for longer dependencies. Also, according to the right confusion matrix, many dependencies are misclassified as elaboration, as shown in the column of elaboration. And elaboration is the most frequent relation in the labeled dataset. So elaboration is can be translated into junsetsu shōsaika in Japanese. And then the second factor of the typical error causes is the inherent ambiguity of discourse relation classes. And for instance, elaboration and progression, or cause effect and explain, are sometimes very difficult to distinguish even for humans. This figure shows the parse tree by AT model. The parser correctly identifies the attachment between the 4 nodes. However, it misclassifies one dependency, column E1 to E2 as explained, though it is cause effect according to the human annotators. And this is a typical errors, classification errors found in the parse output. And last factor of typical errors is domain shift problem. Now, we found that it is still difficult to make discourse dependency parsers adapt to significantly different domains. In this example, the parser misclassifies the dependency from E3 to EDU11 as evaluations, though the content of E11 is not the evaluation result of E3. And we suspect that this is due to the fact that dependencies labeled as evaluation becomes much less frequent in the code 90 dataset, code 90 DT, or biomedical abstract when compared to SciDTB, NLP abstract. And the parser trained on the SciDTB learned that evaluation dependencies tend to appear at the end of the abstracts. I mean, from root to the end, EDUs around the ending position of the abstract. So this is also the typical errors found in the current system. Okay, I would like to conclude this presentation. In this work, we performed comparative analysis of 4 major proxy labeling methods, self-training, co-training, tri-training, and asymmetric training. And we evaluate the algorithms on unsupervised domain adaptation scenario of discourse dependent parsing to biomedical abstracts. And we also built a new discourse dependency tree bank for this problem. And we found that proxy labeling, especially asymmetric tri-training with relaxed agreement criterion, achieves higher parsing accuracies. And it has the potential to reduce manual annotation cost significantly. And we also report typical error causes, 3 typical error causes of current parsing system. And as a future plans, we are currently augmenting code 90 DT by external annotators. We are also planning to examine document properties, which indicate when proxy labeling is effective for discourse dependency parsing. And we are also planning to design annotation schema and parsing method for full-length papers, because this work only use a paper abstract. Okay, so thank you for listening.
Okay, thank you very much. And if you have any questions or comment, please write down in the QA box. And there is one question. Maybe this question is to my presentation. The question is, have you had any useful results about COVID-19 by using this method? Okay. This is very good question. And actually, we have a kind of collaboration with the another American institute related with development of a drug discovery and medical technology platform. And actually, I provided the paper search system I presented to their members, and I hope them to use the paper retrieval. But so far, we haven't got any feedback. And this is just a paper retrieval system. So it is quite difficult to evaluate what kind of how useful result was obtained from the search system. Okay, within the CREST project, one of the members is working on kind of knowledge-based completion system, which aims to infer new information based on the information existing in the existing knowledge base, and also the information extracted from technical papers. Okay, and they applied knowledge-based completion technique. That means that they try to infer some new information which are not directly described neither in knowledge base and paper scientific papers, but the extracted information is quite large, and it's also difficult to evaluate how they are useful. Okay, we can test or simulate that result by deleting some existing knowledge and try the system to be able to infer that deleted information. And in that sense, accuracy looks to be quite good. The accuracy is, they reported accuracy is more than 80%. So the known information could be inferred from the extracted information, but it's quite difficult to evaluate usefulness. So at the moment, we can't report that some useful but unknown information was actually retrieved out by the system. So we hope that that kind of useful result will be obtained by the system we've developed. Okay. Any other questions or comments? Okay, please feel free to write a comment. Okay, there's another question. Okay, I will read that. Can we apply the same method to other language? Okay, for the knowledge extraction task, this partly depends on the annotated data. Okay, so if we can construct the annotation to that language, the same technique is applied because the method which was developed is language independent. Okay, so what about this question to Nishida-san's work?
I see. So yeah, as Matsumoto Sensei says, resource. So I mean the seed data set used in this work is very important, and actually there are several tree banks in other languages. I mean the non-English languages. So in from an abstract point of view, it is possible to apply this method to other languages. However, we need to evaluate actually on the data set to reveal whether this method is independent to English or not. Yeah.
Okay.
For instance, can I add something? In my previous work, I propose an unsupervised parser, and this system strongly depends on the prior knowledge, and the prior knowledge is jumps from by about 9 points, and I think this prior knowledge is strongly depend on the languages, but in the current work, we don't use the prior knowledge. Instead, we use manual annotations. So I think this method is more applicable than this method for other languages.
Okay, thank you. So it looks there is no further question. Thank you very much. I'd like to move to the next talk.
Thank you.
So Terashi-kun, could you share your slide?
Yes. Hello, everyone. Thank you for attending my presentation. I am Hiroki Teranishi, postdoctoral researcher belonging to knowledge acquisition team. Today, I'd like to talk about neural network approaches to coordination disambiguation. Here is the outline of the talk. Let's get started. To begin with, I'll explain what coordination is. Coordination is a syntactic phenomenon where two or more elements, known as conjuncts, are linked together by a coordinator, such as and or. An instance of coordination is called coordinate structure. Coordination looks simple, but highly ambiguous in its structure. For example, in the noun phrase, general managers and designers, we interpret that general modifies managers, not designers. But in the noun phrase, product managers and designers, it is difficult to say that product modifies only managers because product designers also seems to be a correct term. So we have been doing research aimed for resolving structural ambiguities of coordination. Before introducing our approaches, I explain why this research is important. First of all, coordination is a major source of ambiguity in natural language and causes different interpretations among us. Secondly, coordination has many linguistically unique traits and is treated as exceptions in many syntactic series. Thirdly, due to its interactability, coordination is known as a cause of many problems in NLP tasks, such as syntactic parsing, named entity recognition, and machine translation. Lastly, coordination frequently occurs and is observed in about 39 and 61% of the sentences in Pennsylvania and Guinea corpus, respectively. In this presentation, I mainly focus on how we can disambiguate coordination structures. The task of coordination disambiguation is to identify conjunct spans for each coordinator in a sentence. For example, the input sentence shown in this slide has 3 coordinating conjunctions, and the expected output is conjunct spans for each coordinator. The first and second end joins 2 and 3 conjuncts respectively, while but at the beginning of the sentence does not form a coordinate structure within the sentence. The task sounds quite simple, but it's not always easy, even for humans. In the Pennsylvania Bank, for example, this sentence has 5 coordinating conjunctions. Can you imagine which elements are linked by each coordinator? Here is the annotated sentence. You can see one big coordinate structure contains 2 noun phrases, which are followed by relative clauses, and one of them embeds another coordinate structure. So 2 coordinate structures can be either nested or disjoint. In addition, the number of conjuncts in the coordinate structure can be greater than 2, and thus the form of a coordinate structure is not limited to A and B. These complex structures make the task more challenging. For this task, we propose 2 supervised methods, namely the top-down approach and the bottom-up approach. The top-down approach first identifies the entire span of coordination and then splits it into individual conjuncts. A score for each candidate coordination span is computed by neural networks that aim to capture the similarity and replaceability between a pair of conjuncts. I explained these two properties. For the similarity property, it is observed that conjuncts of a coordinate structure tend to have similar meaning and structure. In the example shown in the slide, executives, directors, and other corporate insiders are all noun phrases that mean positions in the company, while purchases and sales are business transactions. The replaceability property means that conjuncts of coordinate structures can be swapped. For example, previous sentence can be said to be as illustrated in the slide. This is the overview of the proposed neural network for the top-down approach. The network consists of 4 layers: input layer, RNN layer, feature extractor, and output layer. The input and RNN layers can be seen as an encoder that maps a sequence of words and part of speech tags into a sequence of contextualized vector representations. The feature extractor produces the feature representation for a candidate coordination span. The output layer computes the score for a given feature representation. I specifically explained the feature extractor. This component produces feature vectors based on the similarity and the replaceability for a coordination span. The similarity feature vectors are computed as element-wise subtraction and multiplication of 2 span vectors, which are average of vectors encoded by the RNN layer, ranging from the beginning of the coordination span to the immediate preceding word before the coordinator, and ranging from the immediate following word after the coordinator to the end of the coordination span. The replaceability feature vectors are computed as subtraction to capture differences between the connectivity of conjuncts and the surrounding contexts. When decoding, the best scoring candidate among all possible spans is chosen as the predicted coordination span for a given coordinator. To get individual conjuncts in the span, it is then split by the coordinator and the comma. For example, the highlighted span is divided into 3 conjuncts. When a sentence has 2 or more coordinators, we choose the best combination of coordination spans, where any of 2 are either nested or disjoint, to avoid conflicts. Our top-down approach achieved the state-of-the-art result, but has a few drawbacks. I briefly compare it with the existing methods. Hara et al. Developed context-free grammar rules to produce coordinate structures. Although their rules are limited, it successfully deals with nested structures and more than 2 conjuncts. They use the discriminative function that incorporates node and edge feature of a sequence alignment to capture similarity between conjuncts. So their method often fails to capture dissimilar conjuncts, such as verb phrases, in spite of laborious feature engineering. Fickler and Goldberg proposed the first neural network-based approach. They used the Berkeley parser to extract candidate conjuncts and then assign the scores to pairs of conjuncts. Their method is more accurate than the method of Hara et al., but it heavily relies on the parser. In addition, their method focuses only on two conjuncts adjacent to a coordinator. In contrast, our top-down approach performs best without such an external parser and can produce more than two conjuncts. However, it can mistakenly divide a coordination span into many conjuncts due to false positive dividing commas. To solve these problems, we alternatively proposed the bottom-up approach, which is the combination of the method of Hara et al. And our neural network model used in the top-down approach. As in the method of Hara et al., this approach produces coordinate structures as a tree because tree structure can express unlimited number of conjuncts and nested structures, and it ensures no partially overlapped spans. Our context-free grammar rules shown in the slide are able to produce 99.5% of coordinate structures in the pen tree rank. The optimal tree for a given sentence can be found efficiently with the CKY algorithm, which is a bottom-up dynamic programming-based parsing algorithm for context-free grammars. In the process of the CKY algorithm, scores for nodes representing spans are computed by neural networks similar to those used in the top-down approach. This is the details of scoring. We define two random variables. One indicates the existence of a conjunct pair, and the other represents the two spans of a conjunct pair. Then we assign log probability of the conjunct pair existence to a node when it derives from a word that can be coordinator and subcoordinator, such as comma and semicolon. When a node derives from two conjuncts, we assign log probability of the occurrence of the two spans. The best split to two conjuncts for a coordination span can be found in cubic time with the CKY algorithm. However, calculating the log probability of different pairs of spans requires quartic time. So instead of doing it straightforwardly, we decompose it into two log probabilities. One represents the occurrence of inner boundaries of the pair, and the other represents the occurrence of outer boundaries. This decomposition reduces the time complexity of the calculation to quadratic time. The three types of probabilities are obtained from three different neural network models. Each model is designed to compute the score for a given observation, and thus models can be trained with minimizing cross-entropy losses with sigmoid or softmax functions. These are our proposed instantiations for the networks. all of which are built on the shared bidirectional LSTM encoder. They are trained jointly in our experiments. Now let's move on to evaluation of the two proposed methods. These are performances evaluated on the Penn tree bank using 4 different agreement criteria. Whole is for matches on coordination span. Outer for matches on 2 outermost conjuncts. Inner for matches on 2 conjuncts adjacent to a coordinator, and exact for matches on all conjuncts. Overall, the proposed bottom-up approach outperforms the top-down approach, but especially on the exact criterion. This is because the bottom-up model learns boundaries for each pair of conjuncts, while the top-down model learns boundaries only for entire coordination spans. We also can see a tendency that the bottom-up approach performs the best on the inner criterion, whereas the top-down approach does on the whole criterion. This is the result of the experiment on the linear tree bank data. Compared with the existing methods, our two approaches perform better for a variety types of phrases. In this result, we find the same tendency observed in the evaluation on the Penn tree bank. This tendency reflects the differences between the algorithms of the two methods. The bottom-up approach builds a coordinate tree in a bottom-up manner and predicts inner conjuncts accurately, whereas the top-down approach predicts the entire span of coordinate structure and then splits it into conjuncts in a top-down manner. We investigate the two approaches for their ability to predict all coordinate structures in a sentence exactly. This result also supports the effectiveness of the context-free grammar production rules and the way of learning conjunct boundaries adapted in the bottom-up approach. These are performances in case of using recently developed contextualized word embeddings in the two approaches. For both approaches, BART and ELMO gave significantly performance gain, while BART contributed much more than ELMO. One of the differences between BART and ELMO lies in their architectures. ELMO embeddings are trained with a bi-LSTM encoder, whereas BART embeddings are trained with a transformer. Because the top-down and bottom-up models employ bi-LSTMs already, the models might benefit more from the transformer, whose attention mechanism can serve as an alignment as used in the previous methods. Following examples from the bottom-up approach are picked for qualitative analysis. Example 1 shows that the system identified the two independent coordinate structures. For the latter coordinate structure, the system correctly predicted adjective phrase coordination of retail and financial, rather than noun phrase coordination of the retail and financial sectors. In example 2, the system successfully captured imbalanced verb phrase coordination of constituents governed by intransitive and transitive verbs. In example 3, the system identified coordinated simple clauses, one of which embeds another coordinate structure. In example 4, however, the system expected that the prepositional phrase at prevailing market prices was included by the right conjunct. The system could not identify the correct head by of the prepositional phrase, while the predicted conjunct was not easily refused because it seemed to be a valid constituent. In example 5, the system predicted the nested noun phrase coordinate structure correctly, but failed to identify the correct causal coordination. This might be caused by the omission of the clause marker that, as seen in the above examples, the system is not good at determining whether phrases around the coordination are included or not by the coordinate structure, while predicted conjuncts by the system tend to be valid as phrases. The bottom-up method must be improved to consider whether the conjuncts have the same relation to peripheral phrases. This is the summary of the two supervised methods for coordination disambiguation. The top-down approach attempts to detect the region of a coordinate structure as a whole, and then retrieve individual conjuncts by dividing it. The bottom-up approach identifies the conjunct pair for each coordinating word and gradually builds coordinate structures so that they do not conflict with each other. Overall, the bottom-up approach outperformed the top-down approach by leveraging conjunct pair learning and global constraints to produce complex coordinate structures. The qualitative analysis revealed that the bottom-up approach suggested promising conjunct spans, and the remaining problems lie in semantic ambiguities rather than grammaticality. In the rest of this presentation, I introduced a concrete application of coordination disambiguation. Named entity recognition is an information extraction task that locates and classifies named entities mentioned in unstructured text into predefined categories such as person names, organizations, and locations. In scientific papers, named entities are often written in coordination expressions to reduce redundancy. For example, named entities human lymphocytes and human B lymphocytes in parallel are expressed as human T and B lymphocytes. Many existing named entity recognizers regard such expression as single large entity, which is no longer identified as original named entities. So we try to extract individual named entities from coordination expressions produced by NER systems. However, supervised methods for coordination disambiguation are not always applicable due to the lack of annotated data in a specific domain. In this realistic scenario, we propose a method that requires no supervision for coordination disambiguation. This method simply finds similar regions into sequences, which is known as the sequence alignment technique for arranging sequences of DNA, RNA, or protein in bioinformatics. A conjunct pair is obtained by finding the best scoring path in the edit graph, where aligning pairs of words are evaluated using cosine similarities of word vectors. We assume that word vectors can be obtained from a language model pre-trained on a large amount of unlabeled text. These are performances of the proposed method. In the evaluation on coordination disambiguation only for noun phrases, the proposed method is far behind supervised method in accuracy. But for the purpose of resolving conjoined named entities, it suffices that the method performs well on simple noun phrases that contain no prepositional phrases or clauses. This is confirmed in the result of any other evaluation. When combined with a named entity recognizer on the top of the BART model pre-trained on biomedical text, the proposed method gives performance gain. When that combination is evaluated only for named entities embedded in elliptical coordination expressions, this only achieves 37.4% of F1 score. But given correct spans of conjoined named entity expressions, it achieves 65% of F1 score, meaning that a large part of errors propagate from the underlying named entity recognizer. Let me conclude this presentation. This talk briefly introduced coordination in NLP. To resolve coordination ambiguities, we developed supervised methods for coordination disambiguation and unsupervised method limited to a specific NLP application, especially on NER. As future work, we will attempt to improve methods for coordination disambiguation with less supervision. Also, we are planning to apply the method to other languages. That's all. Thank you for listening.
Okay, thank you very much. If you have any questions or comments, please write down that in the QA box. And there is one question. Maybe it is a general question, and I will read the question. Is there any advantage of hybridizing part of speech analysis and neural network? I don't quite understand what the question means by hybridizing, but if I can ask about how the part of speech analysis is conducted using neural networks, there are actually quite a few neural network approaches to part of speech analysis. The advantage of using neural network is recently the recurrent network type neural network like LSTM or GRU is quite often used to sequential analysis, and it can actually refer to very long distance information, which was quite difficult when the part of speech tagging is solved by probabilistic method like Markov model, where the long distance informations are quite difficult to incorporate. But recently, as I said, there are lots of neural network methods that can refer to very long distance. And most recent such type of neural network is a transformer-based model, where the transformer originally applied to machine translation, and it uses self-attention within a sentence. So it can refer to all the other words or tokens in a sentence by learning how to attend the important information. So by using such method, pulse width analysis or such information, where most of the useful information exists in the local area, but some information, useful information, may appear in some long distance. So such analysis have obtained a quite huge gain by using neural network. And another tendency is many people now try to use what is called end-to-end method, where they don't like to incorporate any intermediate process or fix the to use such intermediate process may produce some ambiguities or error propagation. So in that sense, some works actually try to avoid such kind of intermediate process like parallel tagging or chunking, so that to apply neural network systems directly as an end-to-end system. So in such approaches, people now get rid of parallel speech analysis anymore. But it depends on the task, I think. Okay, any other questions or comment? Okay, so if you are thinking about the questions, I will introduce the following seminars. Okay, this slide shows the AIP seminars from next week. So every Wednesday afternoon at this time, one of the team will introduce their current research. So please join the seminar, and you have to register the seminar to attend. Okay, it looks that there is no more questions. So I'd like to close this seminar. Okay, thank you very much for attending this seminar. Okay, thank you. Goodbye.